Today's challenge asks us to rearrange numbers in a very specific way. We'll be given a list of numbers, and we need to put them back in an order that follows a particular rule. Take a moment to think. If you had to do this, what would your first idea be? Let's dive into exactly what this problem wants us to do. We're given an array, which you can think of as a numbered list or a row of boxes, each holding a number. The special thing about this array is that it will always have an even number of elements, and half of those elements will be even numbers, while the other half will be odd numbers. For example, if the array has 4 numbers, 2 will be even and 2 will be odd. If it has 10 numbers, 5 will be even and 5 will be odd. Our goal is to rearrange this array so that every even number ends up in an even position, and every odd number ends up in an odd position. Remember, array positions, or indices, usually start counting from 0. So position 0, position 2, position 4, and so on are all even positions. And position 1, position 3, position 5, and so on are all odd positions. Let's look at an example. Imagine our input array is 4, 2, 5, 7. Position 0 holds 4. Position 1 holds 2, position 2 holds 5, and position 3 holds 7. Our target is to have even numbers at even positions and odd numbers at odd positions. So at position 0, which is an even position, we need an even number. 4 is even, so it's good there. At position 1, an odd position, we need an odd number. 2 is even, so it's in the wrong spot. At position 2, an even position, we need an even number. 5 is odd, so it's also in the wrong spot. Finally, at position 3, an odd position, we need an odd number. 7 is odd, so it's good there. A valid output for this example could be 4, 5, 2, 7. Notice how 4 is at index 0 even, 5 is at index 1 odd, 2 is at index 2 even, and 7 is at index 3 odd. All conditions are met. Another valid output could be 2, 5, 4, 7. Or even 4, 7, 2, 5. The exact order of even numbers among themselves or odd numbers among themselves doesn't matter, just that they are in the correct parity match position. What makes this tricky is that we can't just throw numbers anywhere. We have to respect the even-odd pairing of values and their positions. The constraints tell us the array length will be between 2 and 20,000, always even, and the numbers themselves will be between 0 and 1,000. These limits mean we need a solution that works well for a reasonably large list of numbers, not just tiny ones. The most straightforward way to approach this problem, the obvious thing to try first, is to separate all the even numbers from all the odd numbers. Imagine you have a big pile of mixed numbers. You could take 2 empty baskets, label one evens and the other odds. Then you go through your original pile, one number at a time. If a number is even, you toss it into the evens basket. If it's odd, into the odds basket. Once you've gone through all the numbers, you'll have 2 separate collections, one with all even numbers and one with all odd numbers. After sorting them into their respective baskets, the next step is to build our final result array. We know we need an even number at position 0, an odd number at position 1, an even number at position 2, an odd number at position 3, and so on. So we can start filling our new result array. We take the first number from our evens basket and put it at position 0. Then, take the first number from our odds basket and put it at position 1. Next, take the second number from evens and put it at position 2. Then, the second number from odds and put it at position 3. We continue this pattern, alternating between taking an even number for an even position and an odd number for an odd position, until our result array is completely filled. This approach definitely works. It correctly places all even numbers at even positions and all odd numbers at odd positions. However, it requires us to create 2 brand new lists to hold the even and odd numbers temporarily, and then a third new array for the final result. This means we're using extra memory proportional to the size of our original input array. If the original array has n numbers, we're using n extra spaces for the evens and odds lists combined, plus another n spaces for the result array. This is what we call big O of n space complexity. In terms of time, we go through the original array once to sort numbers into evens and odds, and then we go through it again to build the final result. Each pass takes time proportional to n, so overall, it's big O of n time complexity. While big O of n time is generally good, the big O of n space means we're using more memory than strictly necessary. The key insight to optimize this problem is to swap numbers in place directly within the original array without needing extra storage. Instead of creating new lists, we can move numbers around until they are in the correct positions. Think of it like organizing a line of people where boys need to be in even-numbered spots and girls in odd-numbered spots. If you see a boy in an odd spot and a girl in an even spot, you can just have them swap places, and both problems are solved at once. To do this, we'll use a technique called the two-pointer approach. We'll have 2 pointers, which you can imagine as 2 fingers pointing at different spots in our array. Let's call them I and J. Our I pointer will always look for an even number that's in an odd position. It will start at position 0 and then jump 2 steps at a time, looking only at even positions, 0, 2, 4, and so on. Our J pointer will always look for an odd number that's in an even position. It will start at position 1 and jump 2 steps at a time, looking only at odd positions, 1, 3, 5, and so on. We start with I at 0 and J at 1. We will keep moving these pointers as long as they are within the bounds of our array. Inside our main loop, we first check the number at I. If the number at I is already even, that means it's an even number sitting in an even position, since I only points to even positions. This number is correctly placed, so we can move I 2 steps forward to the next even position. We do the same for J. If the number at J is already odd, it's an odd number in an odd position, which is correct. So we move J 2 steps forward to the next odd position. Now what if I finds an odd number at an even position, and J finds an even number at an odd position? This is exactly the mismatch we want to fix. When this happens, we know nums I is an odd number, but I is an even position, and nums J is an even number, but J is an odd position. They are both in the wrong spots, so we simply swap them. We temporarily store nums I in a placeholder, then put nums J into nums I, and finally put the placeholder value into nums J. After the swap, both numbers are now in their correct parity match positions. So we can move both I and J 2 steps forward to continue searching for other misplaced numbers. This process continues until one of our pointers goes past the end of the array, meaning we've checked all relevant positions. Let's trace our optimized 2-pointer approach with the example array 4, 2, 5, 7. The length of our array, n, is 4. We start by setting our 2 pointers, I equals 0 and J equals 1. Our loop continues as long as I is less than n, 4, and J is less than n, 4. First iteration asterisk. Currently, I is 0 and J is 1. Both are less than 4, so we enter the loop. First, we check nums I, which is nums 0. Nums 0 is 4. Is 4 an even number? Yes, 4 divided by 2 has a remainder of 0. Since nums I is even, it's correctly placed at an even index. We advance I by 2, so I becomes 0 plus 2, which is 2. Second iteration asterisk. Now I is 2 and J is 1. Both are still less than 4, so we continue the loop. We check nums I, which is nums 2. Nums 2 is 5. Is 5 an even number? No, 5 divided by 2 has a remainder of 1. So the first condition nums I %2 double equals is equal to 0 is false. We move to the next check. We check nums J, which is nums 1. Nums 1 is 2. Is 2 an odd number? No, 2 divided by 2 has a remainder of 0. So the second condition nums J %2 double equals is equal to 1 is also false. This means we have an odd number at an even position, 5 at index 2, and an even number at an odd position, 2 at index 1. This is the scenario where we need to swap. We perform the swap. We store nums_i, which is 5 in a temporary variable, let's call it temp. So temp equals 5. Then we set nums_i, which is nums2, to nums_j, which is 2. Our array becomes 4, 2, 2, 7. Next we set nums_j, which is nums1, to temp, which is 5. Our array becomes 4, 5, 2, 7. After the swap, both numbers are now correctly placed, so we advance both I and j by 2. I becomes 2 plus 2, which is 4. J becomes 1 plus 2, which is 3. Third iteration asterisk. Now I is 4 and j is 3. Is I less than n 4? No, I is equal to n. The loop condition I n and j n is false because I n is false. The loop terminates. And there's our final result, the array 4, 5, 2, 7. This is correct because at index 0 even we have 4, even, at index 1 odd we have 5, odd, at index 2 even we have 2, even, and at index 3 odd we have 7, odd. You'll often spot the two-pointer pattern when you need to rearrange elements in an array based on some property, especially when you can swap elements directly to fix issues. Another strong signal is when the problem asks you to maintain a specific order or relationship between elements, like all evens before odds or elements less than x on the left, greater than x on the right, without needing extra space. This optimized solution runs in big O of n time because each number is visited and potentially swapped at most once. It achieves big O of 1, constant time space complexity, as we only use a few constant variables for our pointers and a temporary swap. Now that you've seen the two-pointer approach, try another array problem that might benefit from this same pattern. Don't forget to subscribe for more data structures and algorithms explanations.